Hello, and welcome to Calm Science Nights. I'm so glad you're here with me tonight. Before we begin our peaceful journey through the science of the blue sky, if you find comfort in drifting off to the soothing rhythm of light and atmosphere, please consider subscribing to the channel. It helps us create more of these tranquil explorations together. Now, settle into your most comfortable position. Let the weight of the day lift from your shoulders. Tonight, we're going to explore one of nature's most beautiful and familiar mysteries: why the sky is blue. This simple question, one that children ask and adults take for granted, has a story spanning centuries of scientific discovery, from ancient philosophers wondering about the nature of light to modern physicists understanding the quantum dance of photons and molecules. There's no need to remember everything tonight. In fact, there's no need to stay awake at all. Let these words wash over you like gentle waves, each fact a soft ripple in the stream of understanding, carrying you peacefully towards sleep. Just allow the story to unfold at its own unhurried pace, the way light itself travels, swiftly but gracefully, illuminating the world around us. Close your eyes now, and imagine yourself lying in a meadow on a perfect summer afternoon, looking up at a sky of the deepest, clearest blue. That blue has been there since before humans walked the earth, since our planet first had an atmosphere. It's been the backdrop to every moment of human history, yet for most of that history, no one truly understood why the sky wore this particular color. Our story begins, as so many scientific stories do, in ancient Greece, where philosophers first tried to understand the nature of light and color. The Greeks, those patient observers of the natural world, noticed that the sky was blue during the day but turned spectacular shades of red and orange at sunset. They wondered about this transformation, about what light was and why it behaved as it did. But they lacked the tools, both conceptual and physical, to truly understand what they were seeing. Aristotle, the great Greek philosopher who lived in the 4th century BCE, believed that light was not a substance traveling through space but rather a quality or property of transparent materials. When transparent materials like air or water were present between an observer and an object, Aristotle thought, they took on certain qualities that allowed vision to occur. In his view, there was no light traveling from the sun to our eyes. Instead, the presence of the sun activated the potential for vision in the transparent medium of air. This was a beautiful idea in its way, but it was wrong, and it would take nearly 2,000 years for a better understanding to emerge. The ancient Greeks also pondered the nature of color. They generally believed that all colors were mixtures of black and white, darkness and light. The deep blue of the daytime sky might have been understood as air mixed with darkness, or light passing through layers of shadow. These were poetic ideas, attempts to make sense of the world with the philosophical tools available at the time, but they weren't scientific explanations in the sense we would recognize today. It wasn't until the 17th century that the true nature of light began to be understood. Isaac Newton, the English physicist and mathematician whose laws of motion and gravity revolutionized our understanding of the physical world, also made crucial discoveries about light. In a famous series of experiments conducted in the 1660s, Newton passed sunlight through a glass prism and observed that the white light separated into a spectrum of colors: red, orange, yellow, green, blue, indigo, and violet. This was a revelation. White light wasn't pure or simple but was actually a mixture of all the colors of the rainbow. Newton's prism experiments showed that different colors of light behave differently when passing through materials. They refract, or bend, by different amounts. Red light bends least, violet light bends most, with the other colors arranged in between. This suggested that different colors of light have different properties, though Newton didn't know exactly what those properties were. He initially thought of light as composed of tiny particles he called corpuscles, little bullets of light flying through space and bouncing off objects into our eyes. But Newton's contemporary, the Dutch scientist Christian Huygens, had a different idea. Huygens proposed that light was a wave, a disturbance propagating through some medium, similar to how sound waves travel through air or water waves travel across a pond. In the wave theory, different colors corresponded to waves of different wavelengths, the distance between successive peaks of the wave. Red light would have a longer wavelength, violet light a shorter wavelength, with the other colors in between. This debate between the particle and wave theories of light would continue for more than a century, with evidence supporting both views. But for understanding why the sky is blue, the wave theory would prove crucial. If light is a wave with different colors having different wavelengths, then those different wavelengths might interact differently with matter, particularly with the tiny molecules that make up the air. This was the key insight, though it would take until the 19th century for scientists to fully work it out. By the early 1800s, scientists had established that light was almost certainly a wave, not a stream of particles. A series of experiments by Thomas Young and Augustin Jean Fresnel demonstrated interference and diffraction, phenomena that only made sense if light was a wave. When two beams of light overlap, they can reinforce each other or cancel each other out depending on whether their wave peaks align or not. This is called interference, and it's a distinctive property of waves. The understanding that light was a wave raised new questions. What exactly is waving? Ocean waves are oscillations of water, sound waves are oscillations of air pressure. But light can travel through empty space. It reaches us from the sun across 93 million miles of vacuum. What could be waving in empty space? 19th century physicists proposed the existence of a luminiferous ether, an invisible medium filling all of space through which light waves propagated. This ether was thought to be extraordinarily subtle, offering no resistance to the motion of planets and stars, yet rigid enough to support the rapid oscillations of light waves. This brings us to the 1860s and one of the most important breakthroughs in physics, James Clerk Maxwell's unification of electricity and magnetism. Maxwell, a Scottish physicist, realized that electric and magnetic fields could create waves that propagated through space. When an electric field changes, it creates a magnetic field. When that magnetic field changes, it creates an electric field. This back and forth between electric and magnetic fields can propagate as a wave, an electromagnetic wave, and Maxwell calculated that these electromagnetic waves would travel at a specific speed, approximately 300,000 kilometers per second, or about 186,000 miles per second. This speed was exactly the measured speed of light. The conclusion was inescapable: light is an electromagnetic wave. Visible light, Maxwell realized, is just oscillating electric and magnetic fields propagating through space. Different colors of light correspond to different frequencies of oscillation. Red light oscillates about 430 trillion times per second, while violet light oscillates about 750 trillion times per second. The entire rainbow of colors we can see represents electromagnetic waves oscillating at frequencies between these extremes. This was a profound unification. Light, electricity, and magnetism were all aspects of the same fundamental phenomenon. And so our journey has begun with the ancient world's attempts to understand light and color, starting with the Greeks who noticed the sky was blue during the day but turned red and orange at sunset. Aristotle in 4th century BCE believed light was not substance traveling through space but rather quality or property of transparent materials, when transparent materials like air or water present between observer and object, they took on qualities allowing vision to occur. In his view, no light traveling from sun to our eyes. Instead, sun's presence activated potential for vision in transparent air medium. Beautiful idea but wrong. Would take nearly 2,000 years for better understanding to emerge. We learned ancient Greeks pondered color nature, generally believing all colors were mixtures of black and white, darkness and light. Deep blue of daytime sky might have been understood as air mixed with darkness or light passing through shadow layers. These were poetic ideas, attempts to make sense of world with available philosophical tools, but weren't scientific explanations in sense we'd recognize today. We discovered it wasn't until 17th century that light's true nature began being understood. Isaac Newton, English physicist and mathematician whose motion and gravity laws revolutionized physical world understanding, also made crucial light discoveries. In famous 1660s experiment series, Newton passed sunlight through glass prism observing white light separated into spectrum of colors: red, orange, yellow, green, blue, indigo, violet. Revelation. White light wasn't pure or simple but actually mixture of all rainbow colors. We found Newton's prism experiments showed different light colors behave differently when passing through materials. They refract or bend by different amounts. Red light bends least, violet light bends most, other colors arranged in between. Suggested different light colors have different properties, though Newton didn't know exactly what those properties were. Initially thought of light as composed of tiny particles he called corpuscles, little light bullets flying through space and bouncing off objects into our eyes. We met Newton's contemporary, Dutch scientist Christian Huygens, who had different idea. Huygens proposed light was wave, disturbance propagating through some medium similar to how sound waves travel through air or water waves across pond. In wave theory, different colors corresponded to waves of different wavelengths, distance between successive wave peaks. Red light would have longer wavelength, violet light shorter wavelength, other colors in between. We learned this debate between particle and wave light theories would continue for more than a century with evidence supporting both views, but for understanding why sky is blue, wave theory would prove crucial. If light is wave with different colors having different wavelengths, then those different wavelengths might interact differently with matter, particularly with tiny molecules making up air. This was key insight, though would take until 19th century for scientists to fully work it out. We discovered by early 1800s scientists established light almost certainly wave, not particle stream. Experiments series by Thomas Young and Augustin Jean Fresnel demonstrated interference and diffraction, phenomena only making sense if light was wave. When two light beams overlap, can reinforce each other or cancel each other out depending on whether wave peaks align or not, called interference, distinctive wave property. We found understanding that light was wave raised new questions. What exactly is waving? Ocean waves are water oscillations, sound waves are air pressure oscillations, but light can travel through empty space. reaches us from sun across 93 million miles of vacuum, what could be waving in empty space? 19th century physicists proposed luminiferous ether existence, invisible medium filling all space through which light waves propagated, ether thought extraordinarily subtle, offering no resistance to planet and star motion yet rigid enough to support rapid light wave oscillations. We arrived at 1860s in one of physics' most important breakthroughs, James Clerk Maxwell's electricity and magnetism unification. Maxwell, Scottish physicist, realized electric and magnetic fields could create waves propagating through space. When electric field changes creates magnetic field, when that magnetic field changes creates electric field. This back and forth between electric and magnetic fields can propagate as wave, electromagnetic wave, and Maxwell calculated these electromagnetic waves would travel at specific speed, approximately 300,000 kilometers per second or about 186,000 miles per second. We learned this speed was exactly measured light speed. Conclusion inescapable: light is electromagnetic wave. Visible light, Maxwell realized, is just oscillating electric and magnetic fields propagating through space. Different light colors correspond to different oscillation frequencies. Red light oscillates about 430 trillion times per second, while violet light oscillates about 750 trillion times per second. Entire rainbow of colors we can see represents electromagnetic waves oscillating at frequencies between these extremes. Profound unification, light, electricity, and magnetism were all aspects of same fundamental phenomenon. Each fact a gentle step in understanding's slow awakening, the gradual realization that light is not what ancient philosophers imagined but something far more subtle and beautiful, a wave of electric and magnetic fields oscillating through space, with different colors representing different frequencies of oscillation. From Aristotle's misconceptions to Newton's prisms, from Huygens's waves to Maxwell's electromagnetic unification, centuries of patient observation and brilliant insight. Feel yourself in that gradual awakening now, standing with those scientists watching light split into rainbow colors, imagining invisible waves propagating through space, realizing that the blue of the sky must have something to do with how these waves interact with air. The answer is close now, waiting to be discovered. There's nothing to solve tonight, nothing to grasp. Just rest in the gentle beauty of light, in the peaceful understanding that light carries color through space, that the sky above has always been blue for reasons we're only beginning to glimpse. Let the light carry you now, those invisible electromagnetic waves bathing you in gentle illumination, oscillating hundreds of trillions of times per second yet seeming perfectly still and peaceful, drifting gently towards sleep. As we continue our peaceful journey through the story of the blue sky, we move from Maxwell's profound discovery that light is an electromagnetic wave into the next chapter, the realization of how these waves interact with the atmosphere. Understanding that light is a wave was crucial, but it was only half the puzzle. The other half was understanding what happens when these waves encounter the tiny molecules of air that surround our planet. With Maxwell's electromagnetic theory established, scientists in the late 19th century had a clear picture of what light was: oscillating electric and magnetic fields traveling through space at incredible speed. But this raised a new question. If light is a wave passing through the atmosphere, why do we see it at all? When sound waves travel through air, we don't see the air itself, we only hear the sound when it reaches our ears. Why should light be different? Why does the sky glow with color instead of appearing black and transparent? The answer lies in a phenomenon called scattering, the process by which light waves interact with particles or molecules they encounter. When an electromagnetic wave passes near a molecule, the oscillating electric field of the light wave causes the electrons in the molecule to oscillate as well. These oscillating electrons then emit their own electromagnetic waves in all directions. This is scattering. The light is absorbed and re-emitted, sent off in new directions rather than continuing straight through. It's this scattered light, coming at us from all directions in the sky, that makes the sky visible and gives it color. But here's the crucial part, and this is where the story gets truly beautiful. Not all wavelengths of light scatter equally. In the 1870s, the British physicist Lord Rayleigh, John William Strutt, the third Baron Rayleigh, worked out the mathematical theory of how light scatters from particles much smaller than the wavelength of light. What he discovered was elegant and precise. The amount of scattering is inversely proportional to the fourth power of the wavelength. This is called Rayleigh scattering, and it's the key to understanding the blue sky. Let's pause for a moment on what this mathematical relationship means. The fourth power means that small changes in wavelength create enormous differences in scattering. Blue light has a wavelength of about 450 nanometers, while red light has a wavelength of about 650 nanometers. Red light's wavelength is only about 1.4 times longer than blue light's. But when you raise 1.4 to the fourth power, you get about 4, meaning blue light scatters approximately 4 times more strongly than red light. Violet light, with an even shorter wavelength than blue, scatters even more strongly, roughly 5.5 times more than red light. This is why the sky is blue. When sunlight enters Earth's atmosphere, it encounters countless molecules of nitrogen and oxygen, the primary components of air. These molecules are much smaller than the wavelengths of visible light, perfect conditions for Rayleigh scattering. As white sunlight, which remember, is a mixture of all colors, passes through the atmosphere, the blue and violet wavelengths scatter much more strongly than the red, orange, and yellow wavelengths. They bounce off air molecules in all directions, including down toward our eyes. Everywhere we look in the sky, we're seeing this scattered blue and violet light, coming at us from all directions. But if violet light scatters even more strongly than blue light, you might wonder, shouldn't the sky be violet instead of blue? This is an excellent question, and the answer involves the way our eyes perceive color. The human eye has 3 types of color receptors, called cones, which are sensitive to red, green, and blue light. We perceive violet not as a pure sensation but as a combination of blue and a bit of red. Additionally, sunlight doesn't contain equal amounts of all colors. It's actually slightly weighted toward the blue-green part of the spectrum, with somewhat less violet. When we combine the scattering effect, which favors violet, with the composition of sunlight, which has more blue than violet, and the sensitivity of our eyes, which are less sensitive to violet, the result is that the sky appears blue rather than violet. This understanding of Rayleigh scattering, worked out in the 1870s, finally explained why the sky is blue. But Rayleigh's work explained more than just the daytime sky. It also explained why sunsets and sunrises are red and orange. When the sun is low on the horizon at sunrise or sunset, sunlight has to travel through much more atmosphere to reach your eyes than when the sun is overhead. During this long journey through the atmosphere, nearly all the blue light gets scattered away in other directions. What remains, traveling straight through to your eyes, is predominantly the longer wavelengths, the reds, oranges, and yellows that weren't scattered as much. This is why the sun itself appears red at sunset, and why the sky around it glows with warm colors. The same principle explains why clouds are white rather than blue. Clouds are made of water droplets that are much larger than the wavelengths of visible light, typically thousands of nanometers in diameter compared to the 400 to 700 nanometers of visible light. When light encounters particles comparable to or larger than its wavelength, Rayleigh scattering no longer applies. Instead, a different process called Mie scattering takes over. Mie scattering affects all wavelengths of light roughly equally, so all colors scatter together, and the result is white, the combination of all colors. This is why clouds appear white, when they're not too thick, and why fog is white, and why smoke from a fire appears white or gray. Understanding Rayleigh scattering also helps explain variations in sky color under different conditions. On a perfectly clear day with very clean air, the sky can be a deep, saturated blue. But when there's dust, pollution, or water vapor in the air, the sky often appears paler, almost white near the horizon. This is because these larger particles create additional scattering, including some Mie scattering, that washes out the pure blue with scattered white light. The horizon appears paler than the zenith, the point directly overhead, because when you look toward the horizon, you're looking through much more atmosphere, encountering more scattering particles, which creates more white scattered light mixing with the blue. The physics of Rayleigh scattering extends beyond Earth's atmosphere. Any planet or moon with an atmosphere can have a colored sky, and the color depends on the composition of the atmosphere and the spectrum of light from the star it orbits. Mars, for instance, has a thin atmosphere composed mostly of carbon dioxide with suspended dust particles. During the Martian day, when the air is relatively clear, the sky appears butterscotch or tawny colored rather than blue. This is because the fine dust particles suspended in Mars's atmosphere are comparable to the wavelength of light, creating Mie scattering of red light. At sunset on Mars, however, something beautiful and unexpected happens. The sky near the sun turns blue, the opposite of Earth. This occurs because at sunset, sunlight travels through enough atmosphere that Rayleigh scattering of blue light from the CO2 molecules becomes visible, creating a blue glow around the setting sun while the rest of the sky remains reddish. And so we learned with Maxwell's electromagnetic theory established, late 19th century scientists had clear picture of what light was, oscillating electric and magnetic fields traveling through space at incredible speed, but raised new question: if light is wave passing through atmosphere, why do we see it at all? When sound waves travel through air, don't see the air itself, only hear sound when reaches ears. Why should light be different? Why does sky glow with color instead of appearing black and transparent? We discovered answer lies in phenomenon called scattering, process by which light waves interact with particles or molecules they encounter. When electromagnetic wave passes near molecule, oscillating electric field of light wave causes molecule electrons to oscillate as well. These oscillating electrons then emit their own electromagnetic waves in all directions. This is scattering, light absorbed and re-emitted, sent off in new directions rather than continuing straight through. This scattered light coming at us from all sky directions makes sky visible and gives it color. We found crucial part is not all light wavelengths scatter equally. In 1870s British physicist Lord Rayleigh, John William Strutt, 3rd Baron Rayleigh, worked out mathematical theory of how light scatters from particles much smaller than light wavelength. What he discovered was elegant and precise, scattering amount inversely proportional to fourth power of wavelength, called Rayleigh scattering, key to understanding blue sky. We learned this mathematical relationship's meaning. Fourth power means small wavelength changes create enormous scattering differences. Blue light is wavelength about 450 nanometers while red light about 650 nanometers. Red light's wavelength only about 1.4 times longer than blue, but when rays 1.4 to fourth power get about 4, meaning blue light scatters approximately 4 times more strongly than red light. Violet light with even shorter wavelength than blue scatters even more strongly, roughly 5.5 times more than red light. We discovered this is why sky is blue. When sunlight enters Earth's atmosphere and encounters countless nitrogen and oxygen molecules, primary air components, these molecules much smaller than visible light wavelengths, perfect conditions for Rayleigh scattering. As white sunlight, mixture of all colors, passes through atmosphere, blue and violet wavelengths scatter much more strongly than red, orange, and yellow wavelengths, bounce off air molecules in all directions including down toward our eyes. Everywhere we look in sky seeing this scattered blue and violet light coming at us from all directions. We found but if violet light scatters even more strongly than blue, shouldn't sky be violet instead of blue? Excellent question. Answer involves how our eyes perceive color. Human eye has 3 color receptor types, cones, sensitive to red, green, and blue light. We perceive violet not as pure sensation but as combination of blue and bit of red. Additionally, sunlight doesn't contain equal amounts of all colors, actually slightly weighted toward blue-green part of spectrum with somewhat less violet. When combined scattering effect favors violet, with sunlight composition, more blue than violet, and eye sensitivity, less sensitive to violet, result is sky appears blue rather than violet. We learned this Rayleigh scattering understanding worked out in 1870s finally explained why sky is blue, but Rayleigh's work explained more than just daytime sky, also explained why sunsets and sunrises are red and orange. When sun low on horizon at sunrise or sunset, sunlight has to travel through much more atmosphere to reach eyes than when sun overhead. During this long atmosphere journey, nearly all blue light gets scattered away in other directions. What remains traveling straight through to eyes is predominantly longer wavelengths, reds, oranges, yellows that weren't scattered as much. Why sun itself appears red at sunset and why sky around it glows with warm colors. We discovered same principle explains why clouds are white rather than blue. Clouds made of water droplets much larger than visible light wavelengths, typically thousands of nanometers diameter compared to 400 to 700 nanometers of visible light. When light encounters particles comparable to or larger than its wavelength, Rayleigh scattering no longer applies. Instead, different process called Mies scattering takes over. Mies scattering affects all light wavelengths roughly equally so all colors scatter together. Result is white, combination of all colors. Why clouds appear white when not too thick. Why fog is white. Why smoke from fire appears white or gray. We found understanding Rayleigh scattering also helps explain sky color variations under different conditions. On perfectly clear day with very clean air, sky can be deep saturated blue, but when there's dust, pollution, or water vapor in air, sky often appears paler, almost white near horizon. Because these larger particles create additional scattering, including some Mies scattering, washing out pure blue with scattered white light. Horizon appears paler than zenith, point directly overhead, because when looked toward horizon looking through much more atmosphere encountering more scattering particles creating more white scattered light mixing with blue. We learned Rayleigh scattering physics extends beyond Earth's atmosphere. Any planet or moon with atmosphere can have colored sky. Color depends on atmosphere composition and spectrum of light from starred orbits. Mars, for instance, has thin atmosphere, mostly carbon dioxide with suspended dust particles. During Martian day when air relatively clear sky appears butterscotch or tawny colored rather than blue. Because fine dust particles suspended in Mars's atmosphere comparable to light wavelength creating mere scattering of red light. At sunset on Mars, however, something beautiful and unexpected happens. Sky near sun turns blue, opposite of Earth, occurs because at sunset sunlight travels through enough atmosphere that Rayleigh scattering of blue light from CO2 molecules becomes visible, creating blue glow around setting sun while rest of sky remains reddish. Each fact a gentle step in understanding's completion, the gradual realization that sky's blue comes from scattering, from blue light's shorter wavelength making it bounce off air molecules more readily than red light. From Rayleigh's mathematical fourth power law to sunset's red glow, from clouds' white appearance to Mars's butterscotch sky, all following from same elegant principle of how light interacts with matter. Rest in this beautiful understanding now, this recognition that every time you look up at blue sky you're seeing light that is scattered off countless invisible air molecules, bounced and re-emitted in all directions. The blue is real, physical, a consequence of the wavelength of light and the size of molecules. Let yourself drift with this scattered light, these blue photons bouncing off nitrogen and oxygen molecules, coming at you from every direction in the sky, painting the world in peaceful azure, peaceful and unhurried, carried gently towards sleep. As we continue our peaceful journey through the story of the blue sky, we move from the fundamental physics of scattering into deeper explorations of how light interacts with Earth's atmosphere in subtle and beautiful ways. The story of Rayleigh scattering was a triumph of 19th century physics, but as scientists looked more closely at the sky and measured its properties with increasing precision, they discovered additional layers of complexity and wonder. One question that occupied scientists after Rayleigh's work was the exact shade and intensity of the sky's blue. If you look carefully at the sky on a clear day, you'll notice that it's not uniformly blue everywhere. The sky directly overhead, the zenith, appears a deeper, more saturated blue than the sky near the horizon. This gradient of color, from deep blue above to pale blue or even whitish near the edges of your vision, follows naturally from the physics of scattering but reveals something about the path length of light through the atmosphere. When you look straight up, you're looking through the shortest possible path through the atmosphere, perhaps 100 kilometers or so of air between you and space. The light reaching your eyes from this direction has encountered relatively few air molecules, so the blue light you see is relatively pure, dominated by single scattering events. But when you look toward the horizon, you're looking through a much longer atmospheric path, perhaps 30 or 40 times longer, because you're looking through the atmosphere at a shallow angle rather than straight through it. This longer path means the light undergoes multiple scattering events. When light scatters multiple times, the simple fourth power relationship of Rayleigh scattering becomes less dominant. Light that has scattered many times has had more opportunities to be scattered at all wavelengths, which tends to wash out the color, making it whiter. Additionally, any dust, water vapor, or pollution in the atmosphere contributes more scattering near the horizon simply because the light path is so much longer. This is why the horizon sky appears paler and sometimes almost white, while the zenith is a deep, rich blue. Scientists in the late 19th and early 20th centuries worked to measure the exact color and intensity of skylight under different conditions, creating what are called photometric measurements of the sky. These measurements required careful calibration and sophisticated instruments, but they revealed fascinating details. For instance, the polarization of skylight, the orientation of the light waves' oscillations, varies systematically across the sky. Light scattered at 90 degrees from the sun is highly polarized, while light scattered at other angles is less polarized or unpolarized. This polarization pattern in the sky is something that certain animals can detect and use for navigation. Honeybees, for instance, can perceive the polarization of skylight and use it to determine the sun's position even on partly cloudy days when the sun itself is hidden. Some birds and marine animals also navigate using polarization patterns in the sky. Vikings may have used crystals called sunstones, probably calcite or cordierite, that reveal the polarization direction of skylight, allowing them to navigate even when fog or clouds obscured the sun. This natural polarization pattern is a direct consequence of the scattering process. When light scatters from air molecules, the scattered light tends to be polarized perpendicular to the plane containing the incoming light beam and the scattered light beam. Another refinement to the understanding of sky color came in the early 20th century with the development of quantum mechanics. Rayleigh's classical theory of scattering, worked out using electromagnetic wave theory, was remarkably accurate, but it didn't explain scattering in terms of the underlying quantum mechanical processes. In the quantum view, light consists of particles called photons, each carrying a specific amount of energy determined by the light's frequency. Blue photons carry more energy than red photons because blue light has a higher frequency. When a photon encounters an air molecule, the quantum mechanical description of scattering involves the photon being absorbed by the molecule, briefly exciting the electrons to a higher energy state, and then being re-emitted, scattered, as the electrons return to their original state. This process, called Rayleigh scattering in the quantum picture as well, happens more readily for higher energy, shorter wavelength, photons. The quantum mechanical calculation gives exactly the same fourth power dependence on wavelength that Rayleigh derived classically, a beautiful example of how different physical theories can converge on the same result. The quantum understanding of scattering also clarified why the scattering is elastic, why the scattered photon has the same energy and wavelength as the incident photon. In Rayleigh scattering, the molecule returns to exactly the same state it was in before the photon arrived, so the scattered photon must carry away exactly the same energy. This is in contrast to other scattering processes, like Raman scattering, discovered by Indian physicist C.V. Raman in 1928, where the molecule ends up in a different energy state after scattering, and the scattered photon has a different wavelength than the incident photon. The understanding of atmospheric scattering advanced significantly during World War II, when military applications demanded better knowledge of how light propagates through the atmosphere. Visibility through haze, smoke, and fog became critical for targeting and reconnaissance. Scientists developed more sophisticated models of atmospheric scattering that accounted not just for air molecules but for aerosols, tiny particles of dust, salt from ocean spray, pollution, and water droplets suspended in the air. These aerosols complicate the simple picture of Rayleigh scattering because they're often comparable to or larger than the wavelength of light. As we discussed, when particles approach the wavelength of light in size, mass scattering becomes important, and it doesn't have the same strong wavelength dependence as Rayleigh scattering. The presence of aerosols tends to whiten the sky, reducing the purity of the blue. This is why heavily polluted air or air filled with dust or sea spray produces a hazier, whiter sky than clean air. The aerosols are scattering all wavelengths more equally. After the war, this understanding was applied to remote sensing in atmospheric science. By measuring the exact color and intensity of skylight, scientists could infer properties of the atmosphere, its density, the concentration of aerosols, the presence of water vapor. This became especially important with the advent of satellites, which could measure the scattered sunlight from Earth's atmosphere and surface from above, providing global information about air quality, weather patterns, and climate. The study of scattering also extended to understanding other atmospheric phenomena related to the blue sky. For instance, the purple light sometimes seen at twilight, the purple light of the Alps or alpenglow, is caused by a combination of Rayleigh scattering and the scattering of light that has already passed through the stratosphere at very high altitudes. At twilight, when the sun is below the horizon for an observer on the ground, sunlight can still reach the upper atmosphere. This light scatters off the thin air at high altitudes and can create delicate purple and pink hues in the sky, especially over mountains. Another beautiful phenomenon explained by atmospheric scattering is the green flash, a rare optical effect sometimes visible just as the sun sets below a clear ocean horizon. For a second or two, a green spot or ray of light may appear at the top of the sun's disk. This happens because of atmospheric refraction, the bending of light, combined with scattering. The atmosphere acts like a weak prism, splitting sunlight into its component colors. Red light, refracted less, dips below the horizon first. Blue and violet light scatter strongly and are scattered away. What remains for a brief moment, under just the right conditions, is the green light, refracted more than red, less scattered than blue. It's a fleeting glimpse of pure green from the sun, visible only when the atmosphere is very clear and stable. And so we learned one question occupying scientists after Rayleigh's work was exact shade and intensity of sky's blue. If look carefully at sky on clear day, notice it's not uniformly blue everywhere. Sky directly overhead, zenith, appears deeper, more saturated blue than sky near horizon. This color gradient from deep blue above to pale blue or whitish near edges follows naturally from scattering physics but reveals something about light path length through atmosphere. We discovered when looked straight up looking through shortest possible atmosphere path, perhaps 100 kilometers of air between you and space, light reaching eyes from this direction encountered relatively few air molecules, so blue light seen is relatively pure, dominated by single scattering events. But when looked toward horizon looking through much longer atmospheric path, perhaps 30 to 40 times longer because looking through atmosphere at shallow angle rather than straight, longer path means light undergoes multiple scattering events. We found when light scatters multiple times, simple Rayleigh scattering fourth power relationship becomes less dominant. Light scattered many times had more opportunities to be scattered at all wavelengths, tending to wash out color, making it whiter. Additionally, any dust, water vapor, or pollution in atmosphere contributes more scattering near horizon simply because light paths so much longer, Why horizon sky appears paler and sometimes almost white while zenith is deep rich blue. We learned late 19th and early 20th century scientists worked to measure exact skylight color and intensity under different conditions. Creating photometric sky measurements required careful calibration and sophisticated instruments but revealed fascinating details. For instance, skylight polarization, light waves oscillations orientation, varies systematically across sky. Light scattered at 90 degrees from sun highly polarized while light scattered at other angles less polarized or unpolarized. We discovered this sky polarization pattern is something certain animals can detect and use for navigation. Honeybees, for instance, can perceive skylight polarization and use it to determine sun's position even on partly cloudy days when sun itself hidden. Some birds and marine animals also navigate using sky polarization patterns. Vikings may have used crystals called sunstones, probably calcite or cordierite, revealing skylight polarization direction, allowing navigation even when fog or clouds obscured Sunday. Natural polarization pattern, direct consequence of scattering process. When light scatters from air molecules, scattered light tends to be polarized perpendicular to plane containing incoming light beam and scattered light beam. We found another refinement to sky color understanding came in early 20th century with quantum mechanics development. Rayleigh's classical scattering theory worked out using electromagnetic wave theory was remarkably accurate but didn't explain scattering in terms of underlying quantum mechanical processes. In quantum view, light consists of particles called photons, each carrying specific energy amount determined by light's frequency. Blue photons carry more energy than red photons because blue light has higher frequency. We learned when photon encounters air molecule, quantum mechanical scattering description involves photon being absorbed by molecule, briefly exciting electrons to higher energy state, then being re-emitted, scattered, as electrons return to original state. Process called Rayleigh scattering in quantum picture as well, happens more readily for higher energy, shorter wavelength, photons. Quantum mechanical calculation gives exactly same fourth power wavelength dependence that Rayleigh derived classically. Beautiful example of how different physical theories can converge on same result. We discovered quantum scattering understanding also clarified why scattering is elastic, why scattered photon has same energy and wavelength as incident photon. In Rayleigh scattering, molecule returns to exactly same state it was in before photon arrived, so scattered photon must carry away exactly same energy. This in contrast to other scattering processes like Raman scattering, discovered by Indian physicist C.V. Raman in 1928, where molecule ends up in different energy state after scattering and scattered photon has different wavelength than incident photon. We found atmospheric scattering understanding advanced significantly during World War II when military applications demanded better knowledge of how light propagates through atmosphere. Visibility through haze, smoke, fog became critical for targeting and reconnaissance. Scientists developed more sophisticated atmospheric scattering models accounting not just for air molecules but for aerosols, tiny particles of dust, salt from ocean spray, pollution, water droplets suspended in air. We learned these aerosols complicate simple Rayleigh scattering picture because often comparable to or larger than light wavelength. When particles approach light wavelength in size, Ms scattering becomes important. Doesn't have same strong wavelength dependence as Rayleigh scattering. Aerosol presence tends to whiten sky, reducing blue purity. Why heavily polluted air or air filled with dust or sea spray produces hazier, whiter sky than clean air? aerosols scattering all wavelengths more equally. We discovered afterward this understanding applied to remote sensing and atmospheric science. By measuring exact skylight color and intensity, scientists could infer atmosphere properties, density, aerosol concentration, water vapor presence. Became especially important with satellite advent, which could measure scattered sunlight from Earth's atmosphere and surface from above, providing global information about air quality, weather patterns, climate. We found scattering study also extended to understanding other atmospheric phenomena related to blue sky. For instance, purple light, sometimes seen at twilight, purple light of Alps or alpenglow, caused by Rayleigh scattering combination and scattering of light already passed through stratosphere at very high altitudes. At twilight, when sun below horizon for ground observer, sunlight can still reach upper atmosphere. This light scatters off thin high-altitude air and can create delicate purple and pink sky hues, especially over mountains. We learned another beautiful scattering explained phenomenon is green flash, rare optical effect sometimes visible just as sun sets below clear ocean horizon. For a second or two, green spot or light ray may appear at sun's disk top. Happens because of atmospheric refraction, light bending, combined with scattering. Atmosphere acts like weak prism, splitting sunlight into component colors. Red light, refracted less, dips below horizon first. Blue and violet light scatter strongly and scatter away. What remains for brief moment under just right conditions is green light, refracted more than red, less scattered than blue. Fleeting glimpse of pure sun green, visible only when atmosphere very clear and stable. Each fact a gentle step in understanding's deepening. The gradual realization that sky's blue has subtle variations and complexities. From zenith to horizon, from polarization patterns to quantum mechanical photons, from wartime aerosol studies to twilight's purple glow, from green flashes to honeybee navigation, all flowing from same elegant scattering principles. Rest in this layered understanding now. This recognition that the blue sky is not simple but rich with detail. Multiple scattering near horizon, polarized light patterns across the dome of sky, photons briefly exciting molecules before re-emission, all happening constantly above you. Let yourself drift with this scattered light. These countless photons bouncing through the atmosphere, creating gradients of color and patterns of polarization, painting the sky in shades from deep azure to pale white, peaceful and beautiful, carried gently towards sleep. As we continue our peaceful journey through the story of the blue sky, we move from understanding the fundamental scattering processes into exploring how this knowledge transformed our ability to study Earth's atmosphere and beyond. The blue sky, once simply a beautiful mystery, became a scientific tool, a way of reading the invisible composition and structure of the air around us, and eventually, a window into understanding other worlds. In the mid-20th century, as scientists refined their understanding of atmospheric scattering, they began to realize that the exact shade and clarity of the blue sky could tell them things about the atmosphere that weren't directly visible. The amount of blue light reaching the ground, compared to other wavelengths, depends on the total amount of air between the observer and space. This led to the development of techniques for measuring what's called the optical depth or optical thickness of the atmosphere, essentially, how much stuff the light has to pass through. By carefully measuring the intensity of sunlight at different wavelengths, scientists could calculate how much scattering had occurred, and from that, determine the total column of air above them. This technique became particularly important for understanding atmospheric pressure and density at different altitudes. In the 1940s and 1950s, as high-altitude research began with balloons and eventually rockets, direct measurements of the upper atmosphere confirmed what scattering measurements had predicted. The air becomes exponentially thinner with altitude, with most of the atmosphere concentrated in the lowest 10 kilometers. These scattering-based measurements also revealed subtle but important variations in atmospheric composition. For example, the presence of ozone in the stratosphere, which absorbs certain wavelengths of ultraviolet light, could be detected by measuring how sunlight at those wavelengths was diminished. The ozone layer, discovered in the early 20th century, plays a crucial role in protecting life on Earth from harmful UV radiation. Monitoring its thickness and health became possible partly through careful analysis of scattered sunlight. The same blue light that colors our sky also carries information about the protective layer high above. Another application of scattering science emerged in the study of air pollution. As industrial activity increased in the 20th century, many cities experienced severe air quality problems. Smog, a combination of smoke and fog, became a serious health hazard in places like London and Los Angeles. Scientists realized that the haziness and discoloration of the sky in polluted areas was caused by aerosol particles from combustion, industrial processes, and vehicle exhaust. By measuring how these particles scattered light, researchers could quantify pollution levels even before sophisticated chemical analysis was available. The relationship between sky color and air quality became particularly evident in the contrast between clean and polluted air. In pristine environments, remote mountains, polar regions, the open ocean far from land, the sky exhibits a deep, saturated blue that can be almost startling in its intensity. This pure blue indicates air that contains very few aerosol particles, where Rayleigh scattering from air molecules dominates completely. In contrast, urban or industrial areas often have a milky, washed-out sky even on cloudless days, a visible sign that the air is laden with particles that scatter all wavelengths of light more equally. The study of atmospheric scattering also led to a better understanding of optical phenomena that had puzzled observers for centuries. One such phenomenon is the blue moon, not the calendar definition of a second full moon in a month, but the rare optical effect where the moon actually appears blue. This can occur when the atmosphere contains particles of just the right size, typically around 0.6 to 0.9 micrometers in diameter. Such particles, often produced by forest fires or volcanic eruptions, scatter red light more strongly than blue light, the opposite of typical Rayleigh scattering. When moonlight passes through an atmosphere laden with these specific-sized particles, the red light gets scattered away, and the moon can appear distinctly blue or even greenish. The most famous instance of blue moons occurred after the eruption of Krakatoa in Indonesia in 1883. This massive volcanic explosion sent enormous amounts of ash and sulfur dioxide into the stratosphere. The sulfur dioxide combined with water vapor to create tiny sulfuric acid droplets of just the right size to cause red scattering. For months after the eruption, people around the world reported seeing blue and green moons and suns, a global atmospheric effect from a single event. This demonstrated dramatically how atmospheric composition affects the color of light we see, whether from the sky, the sun, or the moon. Understanding atmospheric scattering became essential for astronomy as well. Astronomers have long known that Earth's atmosphere is both a blessing and a curse for observing the cosmos. It protects us and provides the air we breathe, but it also scatters and absorbs light from distant stars and galaxies. The scattered sunlight during the day makes it impossible to see stars. They're still there, still shining, but their faint light is overwhelmed by the bright blue of the scattered sunlight filling the sky. This is why stars are only visible at night when the sun is below the horizon and no longer illuminating the atmosphere above us. But even at night, the atmosphere affects astronomical observations through a phenomenon called airglow. Even in the absence of sunlight, Earth's upper atmosphere emits a faint light caused by chemical reactions, primarily the recombination of oxygen atoms that were split apart by ultraviolet radiation during the day. This airglow is extremely faint, about as bright as the combined light of all the stars in the sky, but it's enough to limit the sensitivity of ground-based telescopes. The airglow has its own color spectrum, with green being particularly prominent due to emission from oxygen atoms. This is different from scattered light, it's actual light emission, but it's another way the atmosphere glows and creates background light that astronomers must contend with. The desire to escape atmospheric scattering and absorption was one of the driving forces behind space-based astronomy. When telescopes are placed above the atmosphere, they can observe the universe without the interference of scattered light, atmospheric absorption, or the turbulence that makes stars twinkle. The Hubble Space Telescope, launched in 1990, revolutionized astronomy partly because it could observe in wavelengths that Earth's atmosphere blocks and partly because its images weren't contaminated by scattered light. From space, the daytime sky is black, and stars are visible even when the sun is in view, a perspective impossible from Earth's surface where the blue sky dominates. The principles of atmospheric scattering discovered through studying Earth's blue sky have been applied to understanding other planets and moons in our solar system. Every world with an atmosphere scatters light in ways that reveal the atmosphere's composition and structure. Venus, shrouded in thick clouds of sulfuric acid, appears brilliant white from space because its clouds reflect and scatter nearly all the sunlight that hits them. The pale yellow color of Venus's sky as seen from the surface, captured by Soviet Venera landers in the 1970s and 1980s, results from the scattering properties of the carbon dioxide atmosphere and the sulfuric acid cloud particles. Saturn's moon Titan, the only moon in the solar system with a substantial atmosphere, has an orange sky. Titan's thick nitrogen atmosphere contains organic compounds called tholins, complex hydrocarbons created by solar radiation breaking apart methane and nitrogen molecules. These tholins are reddish-orange and exist as tiny aerosol particles throughout the atmosphere. They scatter light in a way that gives Titan's sky its distinctive orange hue, similar to how Earth would look during a severe dust storm, but as a permanent condition. The Huygens probe, which landed on Titan in 2005, confirmed this orange sky and provided the first direct measurements of scattering in an alien atmosphere. And so we learned in mid-20th century as scientists refined atmospheric scattering understanding, began realizing exact shade and clarity of blue sky could tell them things about atmosphere not directly visible. Amount of blue light reaching ground compared to other wavelengths depends on total air amount between observer and space. This led to developing techniques for measuring what's called optical depth or optical thickness of atmosphere, essentially how much stuff light has to pass through. We discovered by carefully measuring sunlight intensity at different wavelengths scientists could calculate how much scattering occurred and from that determine total air column above them. Technique became particularly important for understanding atmospheric pressure and density at different altitudes. In 1940s to 1950s, as high-altitude research began with balloons and eventually rockets, direct upper atmosphere measurements confirmed what scattering measurements predicted. Air becomes exponentially thinner with altitude, with most atmosphere concentrated in lowest 10 kilometers. We found scattering-based measurements also revealed subtle but important atmospheric composition variations. For example, stratosphere ozone presence absorbs certain UV light wavelengths, could be detected by measuring how sunlight at those wavelengths was diminished. Ozone layer discovered early 20th century plays crucial role protecting Earth life from harmful UV radiation. Monitoring its thickness and health became possible partly through careful scattered sunlight analysis. Same blue light coloring our sky also carries information about protective high-altitude layer. We learned another scattering science application emerged in air pollution study. As 20th century industrial activity increased, many cities experienced severe air quality problems. Smog, smoke and fog combination, became serious health hazard in places like London and Los Angeles. Scientists realized haziness and sky discoloration in polluted areas caused by aerosol particles from combustion, industrial processes, vehicle exhaust. By measuring how these particles scattered light, researchers could quantify pollution levels even before sophisticated chemical analysis available. We discovered relationship between sky color and air quality became particularly evident in clean and polluted air contrast. In pristine environments, remote mountains, polar regions, open ocean far from land, sky exhibits deep saturated blue that can be almost startling in intensity. This pure blue indicates air containing very few aerosol particles, where Rayleigh scattering from air molecules dominates completely. In contrast, urban or industrial areas often have milky washed-out sky even on cloudless days, visible sign air laden with particles scattering all light wavelengths more equally. We found atmospheric scattering study also led to better understanding of optical phenomena puzzling observers for centuries. One such phenomenon is blue moon, not calendar definition of second full moon and month, but rare optical effect where moon actually appears blue. Can occur when atmosphere contains particles of just right size, typically around 0.6 to 0.9 micrometers diameter. Such particles, often produced by forest fires or volcanic eruptions, scatter red light more strongly than blue light, opposite of typical Rayleigh scattering. When moonlight passes through atmosphere laden with these specific sized particles, red light gets scattered away and moon can appear distinctly blue or even greenish. We learned most famous blue moon instance occurred after Krakatoa eruption in Indonesia in 1883. Massive volcanic explosion sent enormous ash and sulfur dioxide amounts into stratosphere. Sulfur dioxide combined with water vapor, creating tiny sulfuric acid droplets of just right size to cause red scattering. For months after eruption, people worldwide reported seeing blue and green moons and suns. Global atmospheric effect from single event demonstrating dramatically how atmospheric composition affects light color we see, whether from sky, sun, or moon. We discovered understanding atmospheric scattering became essential for astronomy. Astronomers long knew Earth's atmosphere, both blessing and curse for observing cosmos, protects us, provides air we breathe, but also scatters and absorbs light from distant stars and galaxies. Scattered sunlight during day makes seeing stars impossible. They're still shining, but their faint light overwhelmed by bright blue scattered sunlight filling sky. Why stars only visible at night when sun below horizon no longer illuminating atmosphere above us? We found, but even at night atmosphere affects astronomical observations through phenomenon called airglow. Even absent sunlight, Earth's upper atmosphere emits faint light caused by chemical reactions, primarily recombination of oxygen atoms split apart by daytime ultraviolet radiation. Airglow extremely faint, about as bright as combined light of all sky stars, but enough to limit ground-based telescope sensitivity. Has own color spectrum with green particularly prominent due to oxygen atom emission, different from scattered light, actual light emission, but another way atmosphere glows, creating background light astronomers must contend with. We learned desire to escape atmospheric scattering and absorption was driving force behind space-based astronomy. Telescopes placed above atmosphere can observe universe without scattered light interference, atmospheric absorption, or turbulence making stars twinkle. Hubble Space Telescope, launched 1990, revolutionized astronomy partly because could observe in wavelengths Earth's atmosphere blocks and partly because images not contaminated by scattered light from space. Daytime sky is black, stars visible even when sun in view, perspective impossible from Earth's surface where blue sky dominates. We discovered atmospheric scattering principles discovered through studying Earth's blue sky applied to understanding other solar system planets and moons. Every world with atmosphere scatters light in ways revealing atmosphere composition and structure. Venus, shrouded in thick sulfuric acid clouds, appears brilliant white from space because clouds reflect and scatter nearly all hitting sunlight. Pale yellow Venus sky color seen from surface, captured by Soviet Venera landers 1970s to 1980s, results from carbon dioxide atmosphere and sulfuric acid cloud particle scattering properties. We found Saturn's moon Titan, only solar system moon with substantial atmosphere, has orange sky. Titan's thick nitrogen atmosphere contains organic compounds called tholins, complex hydrocarbons created by solar radiation breaking apart methane and nitrogen molecules. These reddish-orange tholins exist as tiny aerosol particles throughout atmosphere, scatter light, giving Titan's sky distinctive orange hue, similar to how Earth would look during severe dust storm but as permanent condition. Huygens probe landed on Titan 2005 confirmed orange sky, provided first direct alien atmosphere scattering measurements. Each fact a gentle step in understanding's expansion, the gradual realization that blue sky is not just beautiful but informative, revealing atmospheric density, composition, pollution levels. From optical depth measurements to ozone layer monitoring, from blue moons after volcanic eruptions to airglow limiting astronomy, from space telescopes escaping atmospheric scattering to Titan's orange sky, all flowing from same scattering principles. Rest in this profound utility now, this recognition that the blue sky is both aesthetic wonder and scientific instrument. The same scattering that creates beauty also creates information, allowing us to read the invisible atmosphere, to monitor pollution, to understand other worlds. Let yourself drift with this scattered light carrying information, these photons bouncing off molecules and aerosols telling stories about the air around us, painting sky in shades from deep blue to milky white to orange, peaceful and informative, carried gently towards sleep. As we continue our peaceful journey through the story of the blue sky, we move into more recent discoveries and applications, exploring how our understanding of atmospheric scattering has deepened in the age of satellites and climate science, and how the blue sky connects to some of the most pressing environmental questions of our time. The simple wonder of a blue sky has become intertwined with our ability to monitor and understand the health of our planet. One of the most important applications of scattering science in recent decades has been in climate research. The same aerosol particles that affect the color and clarity of the sky also play a crucial role in Earth's energy balance and climate. Aerosols can both cool and warm the planet through different mechanisms. Light-colored aerosols like sulfates, which come from volcanic eruptions and industrial pollution, scatter sunlight back into space before it can warm Earth's surface, producing a cooling effect. Dark aerosols like black carbon from incomplete combustion absorb sunlight, warming the atmosphere and contributing to heating. Satellites equipped with sophisticated instruments now constantly monitor the scattering properties of Earth's atmosphere from space. These instruments measure sunlight scattered by aerosols and clouds, allowing scientists to create global maps of aerosol distribution and concentration. This information is crucial for understanding climate change because aerosols have a complex and sometimes counterintuitive effect on temperature. During the mid-20th century, when industrial pollution was at its peak in many countries, the cooling effect of aerosols may have temporarily masked some of the warming caused by greenhouse gases. As air quality regulations reduced aerosol pollution in many regions, this masking effect diminished, allowing more of the greenhouse warming to become apparent. The study of how aerosols scatter and absorb light has also revealed their influence on cloud formation, which adds another layer of complexity to climate science. Aerosols serve as cloud condensation nuclei, the tiny particles around which water vapor condenses to form cloud droplets. More aerosols in the atmosphere generally mean more but smaller cloud droplets, which makes clouds brighter and more reflective, another cooling effect. This is visible from space as ship tracks, bright lines of clouds that form in the wake of ships crossing the ocean, created by aerosol particles from ship exhaust serving as additional cloud condensation nuclei. Understanding these aerosol effects requires precise measurements of how particles of different sizes and compositions scatter light at different wavelengths. Scientists use instruments called sun photometers placed around the world to measure the intensity of sunlight reaching the ground at specific wavelengths. By analyzing how much light is scattered or absorbed at each wavelength, they can determine the amount and type of aerosols in the atmosphere above that location. This global network of sun photometers, called AeroNet, Aerosol Robotic Network, provides continuous monitoring of atmospheric aerosols and contributes crucial data for climate models. The connection between sky color and atmospheric composition has also become relevant in monitoring wildfires, which have become more frequent and intense in many regions due to climate change. Large wildfires inject enormous amounts of smoke particles into the atmosphere, sometimes reaching the stratosphere where they can persist for months. These smoke particles can travel thousands of miles from their source, affecting sky color across entire continents. After major wildfires in Australia, Canada, or the western United States, people thousands of miles away have reported seeing hazy, orange-tinted skies, or even vivid red suns similar to those seen after volcanic eruptions. The 2020 wildfires in the western United States provided a dramatic example of how wildfire smoke affects sky color. In September 2020, residents of San Francisco woke to skies that appeared orange, almost apocalyptic in their strangeness. The sun, when visible through the smoke, appeared as a dim red disk. This eerie light resulted from smoke particles high in the atmosphere scattering away the shorter blue wavelengths while allowing the longer red and orange wavelengths to pass through. It was essentially an extended sunset effect lasting all day, a testament to the massive amount of particulate matter suspended in the air. Measurements showed that the smoke layer was thick enough to scatter and absorb most of the visible light, reducing the amount of sunlight reaching the surface by more than 50%. Beyond Earth, the principles of light scattering continue to inform our exploration of other worlds. When spacecraft visit planets or moons, one of the first things scientists examine is the color and scattering properties of their atmospheres, if they have them. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, made detailed measurements of the scattering properties of Titan's atmosphere, revealing subtle variations with altitude and season. These measurements showed that Titan's atmospheric haze is produced continuously by photochemical reactions and gradually settles toward the surface, creating a complex layered atmosphere. More recently, the study of atmospheric scattering has extended to exoplanets, planets orbiting other stars. When an exoplanet passes in front of its star, an event called a transit, a tiny fraction of the starlight passes through the planet's atmosphere before reaching us. By measuring how the spectrum of this light changes as it passes through the atmosphere, scientists can determine what gases are present and how the atmosphere scatters light. This technique, called transmission spectroscopy, has revealed atmospheres around dozens of exoplanets, some with clouds, some with hazes, and some with clear skies. For exoplanets, detecting Rayleigh scattering in transmission spectra is particularly valuable because it provides information about the atmosphere's composition and the size of atmospheric particles without requiring detailed knowledge of the planet's atmospheric structure. The characteristic fourth-power wavelength dependence of Rayleigh scattering creates a distinctive signature in the spectrum, more scattering at shorter wavelengths, making the planet appear slightly larger when observed in blue light than in red light. When this signature is detected, it indicates that the upper atmosphere contains small particles or molecules, similar to Earth's air. Some of the most intriguing exoplanet discoveries involve worlds with skies that would appear dramatically different from Earth's. HD 189733b, a Jupiter-sized planet orbiting very close to its star, has an atmosphere containing silicate particles that scatter blue light, giving the planet a deep blue color when viewed from space, though for a very different reason than Earth's blue sky. The blue color comes from Rayleigh scattering by tiny particles of silicate glass in the planet's scorching atmosphere, where temperatures exceed 1000 degrees Celsius. If you could somehow stand in that atmosphere, the sky might appear blue, but you'd be vaporized almost instantly by the extreme heat and pressure. Other exoplanets have been found with atmospheric hazes made of photochemical smog, similar to Titan but around planets quite different from Titan. Some of these hazy worlds orbit red dwarf stars, which emit most of their light at longer, redder wavelengths than our Sun. On a planet orbiting a red dwarf, if the atmosphere scattered light like Earth's does, the sky might appear orange or red rather than blue, simply because the star's light contains more red than blue to begin with. The exact color would depend on the complex interplay between the star's spectrum, the atmosphere's composition, and the scattering properties of atmospheric particles. And so we learned one of most important scattering science applications in recent decades has been in climate research. Same aerosol particles affecting sky color and clarity also play a crucial role in Earth's energy balance and climate. Aerosols can both cool and warm planet through different mechanisms. Light-colored aerosols like sulfates, from volcanic eruptions and industrial pollution, scatter sunlight back into space before it can warm Earth's surface, producing cooling effect. Dark aerosols like black carbon from incomplete combustion absorb sunlight, warming atmosphere, contributing to heating. We discovered satellites equipped with sophisticated instruments now constantly monitor Earth's atmosphere scattering properties from space. Instruments measure sunlight scattered by aerosols and clouds, allowing scientists to create global aerosol distribution and concentration maps. Information crucial for understanding climate change because aerosols have complex, sometimes counterintuitive temperature effect. During mid-20th century, when industrial pollution at peak in many countries, aerosol cooling effect may have temporarily masked some greenhouse gas warming. As air quality regulations reduced aerosol pollution in many regions, masking effect diminished, allowing more greenhouse warming to become apparent. We found study of how aerosols scatter and absorb light also revealed their cloud formation influence, adding another climate science complexity layer. Aerosols serve as cloud condensation nuclei, tiny particles around which water vapor condenses, forming cloud droplets. More atmospheric aerosols generally mean more but smaller cloud droplets, making clouds brighter and more reflective. Another cooling effect, visible from space as ship tracks, bright cloud lines forming in wake of ocean-crossing ships, created by ship exhaust aerosol particles serving as additional cloud condensation nuclei. We learned understanding these aerosol effects requires precise measurements of how different size and composition particles scatter light at different wavelengths. Scientists use sun photometers placed worldwide to measure ground-reaching sunlight intensity at specific wavelengths. By analyzing how much light scattered or absorbed at each wavelength can determine amount and type of aerosols in atmosphere above that location. This global sun photometer network, called AeroNet, Aerosol Robotic Network, provides continuous atmospheric aerosol monitoring, contributing crucial climate model data. We discovered connection between sky color and atmospheric composition also became relevant in wildfire monitoring, which have become more frequent and intense in many regions due to climate change. Large wildfires inject enormous smoke particle amounts into atmosphere, sometimes reaching stratosphere where can persist for months. Smoke particles can travel thousands of miles from source, affecting sky color across entire continents. After major wildfires in Australia, Canada, or western United States, people thousands of miles away reported seeing hazy orange-tinted skies or even vivid red suns similar to those seen after volcanic eruptions. We found 2020 wildfires in western United States provided dramatic example of how wildfire smoke affects sky color. September 2020, San Francisco residents woke to orange skies, almost apocalyptic in strangeness. Sun, when visible through smoke, appeared as dim red disk. Eerie light resulted from high atmosphere smoke particles scattering away shorter blue wavelengths while allowing longer red and orange wavelengths to pass through, essentially extended all-day sunset effect, testament to massive amount of suspended particulate matter. Measurements showed smoke layer thick enough to scatter and absorb most visible light, reducing surface reaching sunlight by more than 50%. We learned beyond Earth light scattering principles continue informing exploration of other worlds. When spacecraft visit planets or moons, one of first things scientists examine is their atmosphere's color and scattering properties if they have them. Cassini spacecraft orbiting Saturn 2004 to 2017 made detailed Titan atmosphere scattering property measurements revealing subtle altitude and season variations. Measurements showed Titan's atmospheric haze produced continuously by photochemical reactions gradually settling towards surface, creating complex layered atmosphere. We discovered more recently atmospheric scattering study extended to exoplanets, planets orbiting other stars. When exoplanet passes in front of its star, transit event, tiny starlight fraction passes through planet's atmosphere before reaching us. By measuring how this light spectrum changes passing through atmosphere, scientists can determine what gas is present and how atmosphere scatters light. Technique called transmission spectroscopy revealed atmospheres around dozens of exoplanets, some with clouds, some with hazes, some with clear skies. We found for exoplanets detecting Rayleigh scattering in transmission spectra particularly valuable because provides information about atmosphere composition and atmospheric particle size without requiring detailed atmospheric structure knowledge. Characteristic Rayleigh scattering fourth power wavelength dependence creates distinctive spectrum signature. More scattering at shorter wavelengths, making planet appear slightly larger when observed in blue light than red light. When signature detected indicates upper atmosphere contains small particles or molecules similar to Earth's air. We learned some most intriguing exoplanet discoveries involve worlds with skies appearing dramatically different from Earth's. HD 189733b. Jupiter-sized planet orbiting very close to its star, has atmosphere containing silicate particles scattering blue light, giving planet deep blue color when viewed from space, though for very different reason than Earth's blue sky. Blue color comes from Rayleigh scattering by tiny silicate glass particles in planet's scorching atmosphere where temperatures exceed 1000 degrees Celsius. If could somehow stand in that atmosphere, sky might appear blue, but you'd be vaporized almost instantly by extreme heat and pressure. We discovered other exoplanets found with atmospheric hazes made of photochemical smog similar to Titan but around quite different planets. Some hazy worlds orbit red dwarf stars emitting most light at longer, redder wavelengths than our Sun. On planet orbiting red dwarf, if atmosphere scattered light like Earth's does, sky might appear orange or red rather than blue simply because star's light contains more red than blue to begin with. Exact color would depend on complex interplay between star's spectrum, atmosphere composition, and atmospheric particle scattering properties. Each fact a gentle step in understanding's modern applications. The gradual realization that blue sky science now serves climate research, wildfire monitoring, exoplanet characterization. From satellite aerosol measurements to ship track clouds, from orange San Francisco skies to blue exoplanet HD 189733b, from Aranet sun photometers to transmission spectroscopy, all flowing from same scattering principles. Rest in this expanded understanding now, this recognition that blue sky is not just local phenomenon but window into planetary atmospheres everywhere. The same scattering creating Earth's blue also reveals climate changes, monitors wildfires, characterizes alien worlds. Let yourself drift with this universal scattering. These photons bouncing off particles on Earth and on distant worlds, creating skies of blue and orange and red, carrying information across space, peaceful and cosmic, carried gently towards sleep. As we approach the end of our peaceful journey through the story of the blue sky, we turn to the final questions: how our understanding of scattering has deepened our appreciation of light itself, what the quantum nature of light reveals about why the sky is blue, and what this simple everyday phenomenon teaches us about the nature of reality. The blue sky, which seemed so simple a question at the beginning, has led us on a journey through centuries of physics, from ancient philosophy to quantum mechanics to climate science. One of the beautiful aspects of the blue sky that we haven't yet fully explored is how it demonstrates the wave nature of light in a way that's accessible to anyone who simply looks up. The very fact that different colors scatter differently, that blue scatters more than red, is direct evidence that light behaves as a wave with different wavelengths. If light were simply particles with no wave properties, there would be no reason for blue light to behave differently from red light when encountering air molecules. The fourth power dependence on wavelength in Rayleigh scattering is a distinctly wave phenomenon, a relationship that emerges from how oscillating electromagnetic fields interact with matter. Yet modern physics tells us that light is both wave and particle, a concept called wave-particle duality that was one of the revolutionary insights of quantum mechanics in the early 20th century. Photons, the particle manifestation of light, carry energy proportional to their frequency. Blue photons, oscillating more rapidly than red photons, carry more energy. When these photons interact with air molecules in the quantum description of Rayleigh scattering, the higher energy blue photons are more effective at inducing the oscillations in the electron clouds that lead to scattering. It's the same process described by Lord Rayleigh in the 1870s but understood at a deeper, more fundamental level. This quantum understanding connects to a broader realization about the nature of color itself. Color, as we perceive it, doesn't exist in the physical world, not really. What exists are electromagnetic waves of different frequencies, oscillating electric and magnetic fields propagating through space. Color is something our brains construct from the signals our eyes send when different wavelengths stimulate the cone cells in our retinas. The blue of the sky is an interpretation, a creation of consciousness, though it's based on real physical properties, the wavelength of the scattered light reaching our eyes. Different animals with different visual systems would perceive the sky differently. Birds, which can see ultraviolet light, perceive sky colors we cannot imagine. The study of how we perceive the blue sky has also revealed interesting aspects of human color vision and perception. Our eyes are not equally sensitive to all wavelengths of light. We're most sensitive to green light, somewhat less sensitive to blue and red, and considerably less sensitive to violet. This is why the sky appears blue rather than violet, even though violet light scatters even more strongly. Additionally, the sun's spectrum peaks in the green-yellow part of the spectrum, not in the blue or violet. Our eyes evolved under sunlight, and our peak sensitivity matches reasonably well with the sun's peak output. This is not a coincidence but rather the result of natural selection optimizing our vision for the light available on Earth. The perception of the blue sky also demonstrates a phenomenon called color constancy, our brain's ability to perceive colors as relatively stable even when the illumination changes. The light from the sky is distinctly blue, yet when this blue light illuminates objects around us, we don't perceive everything as blue. Our visual system compensates, extracting information about the object's true colors even when they're lit by colored light. This sophisticated processing happens unconsciously and constantly, allowing us to navigate a world where the illumination is always changing, from the blue light of open sky to the red-orange light of sunset to the artificial light of indoor spaces. Interestingly, the blue sky has played a role in artistic movements and the development of painting techniques throughout history. Before the 19th century, many painters depicted skies in relatively flat, uniform blues or with stylized clouds but without much attention to the subtle gradations and variations of real atmospheric light. The Impressionist movement of the late 1800s, happening around the same time that Rayleigh was working out the physics of scattering, brought a new attention to the actual appearance of sky and atmosphere. Painters like Claude Monet studied how the sky changes color from zenith to horizon, how it appears different at different times of day, how atmospheric haze affects the appearance of distant objects. The Impressionists' interest in capturing the fleeting effects of light and atmosphere paralleled the scientific understanding developing at the same time. Both artists and scientists were paying close attention to the same phenomena: the scattering of light, the color of shadows, the effects of atmospheric perspective. The blue shadows in Monet's snow scenes, which seemed revolutionary to contemporary viewers, are actually physically accurate. Snow and shade is illuminated primarily by blue skylight rather than direct yellow sunlight, so shadows on snow really are blue. The Impressionists were painting the physics of light scattering, whether they knew it or not. This connection between art and science and understanding the blue sky reminds us that there are different ways of knowing the world. The physicists' understanding of Rayleigh scattering and the fourth power law is one way of comprehending the blue sky: precise, mathematical, predictive. The artist's understanding, how the blue shifts and changes, how it interacts with other colors, how it creates mood and atmosphere, is another way, equally valid, equally true to the phenomenon. Both kinds of understanding enrich our experience of looking up at the sky. As we've learned throughout this journey, the blue sky is also a reminder of our planet's uniqueness and the delicate balance that makes Earth habitable. The presence of an atmosphere with just the right composition, mostly nitrogen and oxygen, in just the right proportions, at just the right pressure, is what creates our blue sky. It's also what protects us from harmful radiation, moderates our temperature, provides the air we breathe, and enables the water cycle that sustains life. The blue sky is a visible sign of the invisible atmosphere that makes our planet a home. Looking to the future, our understanding of atmospheric scattering continues to evolve and find new applications. Scientists are developing ever more sophisticated models of how light interacts with Earth's complex, changing atmosphere, accounting not just for simple Rayleigh and Mie scattering but for multiple scattering events, for the effects of clouds at different altitudes, for the influence of atmospheric chemistry. These models are essential for climate science, for weather prediction, for interpreting satellite data, and for understanding how our planet's atmosphere might change in the future. There's also growing interest in using the principles of atmospheric scattering for geoengineering, deliberately modifying the atmosphere to combat climate change. Some proposals involve injecting aerosols into the stratosphere to increase the scattering of sunlight back to space, mimicking the cooling effect of large volcanic eruptions. Such interventions would literally change the color of the sky, potentially making it whiter or hazier, reducing the deep blue that we're accustomed to. Whether such dramatic interventions are wise or necessary remains deeply controversial, but the fact that they're even being seriously discussed shows how far our understanding of atmospheric scattering has come since Lord Rayleigh's time. In our search for life beyond Earth, the blue sky has also become a potential biosignature, a sign that might indicate the presence of life on a distant planet. An atmosphere rich in oxygen, like Earth's, would scatter light in distinctive ways. If we could detect this scattering signature in the atmosphere of an exoplanet, it might suggest that photosynthetic organisms are producing oxygen, as they do on Earth. The blue sky, in this sense, is not just beautiful but potentially diagnostic, a visible sign of the biological activity that has transformed our planet's atmosphere over billions of years. And so our journey through the blue sky comes to its end, though the sky itself continues above us, scattering light as it has for as long as Earth has had an atmosphere. We've traveled from ancient Greek philosophers who wondered about the nature of light and color, through Newton's prism experiments that revealed white light as a mixture of colors, to Maxwell's discovery that light is an electromagnetic wave, to Rayleigh's mathematical explanation of why shorter wavelengths scatter more strongly than longer ones. We've learned that the sky is blue because blue light, with its shorter wavelength of about 450 nanometers, scatters approximately 4 times more strongly than red light when it encounters the nitrogen and oxygen molecules in Earth's atmosphere. This scattering, called Rayleigh scattering, follows a fourth power dependence on wavelength, an elegant mathematical relationship that emerges from the interaction of electromagnetic waves with particles much smaller than the wavelength of light. We've discovered that the same physics explains why sunsets are red. The long path through the atmosphere scatters away the blue light, leaving the red and orange. Why clouds are white. Large water droplets scatter all colors equally through Mie scattering. Why the horizon appears paler than the zenith. Multiple scattering events wash out the color. Why Mars has a butterscotch sky while Titan's is orange. Different atmospheric compositions and particle sizes create different scattering. We've seen how the blue sky became a scientific tool for measuring atmospheric properties, for monitoring pollution and climate change, for detecting ozone and aerosols. How wildfire smoke can turn the sky orange for thousands of miles. How the same scattering principles apply to exoplanets orbiting distant stars, where skies might be blue from silicate glass particles or red from a red dwarf's light. We've understood that the blue sky demonstrates the wave nature of light, yet light is also made of photons with particle properties. That color is something our brains construct from electromagnetic waves of different frequencies. That our eyes evolved to be most sensitive to the wavelengths that are most abundant in sunlight. That artists and scientists have both studied the sky's colors, each contributing different kinds of understanding. As you rest now, know that you carry this understanding with you. Every time you look up at a blue sky, you're seeing the result of countless scattering events, photons from the sun bouncing off nitrogen and oxygen molecules, the shorter blue wavelengths scattering more strongly, coming at you from all directions to paint the dome of the sky in peaceful azure. You're seeing light that has traveled 93 million miles from the sun in about 8 minutes, then scattered off invisible molecules in the last tiny fraction of its journey. You're seeing physics in action, the electromagnetic force at work, quantum mechanics manifesting in the everyday world. You're seeing the same phenomenon that creates red sunsets and white clouds, that allows us to monitor our planet's climate, that helps us search for life on distant worlds. The blue sky is a gift of physics, of chemistry, of the particular composition of Earth's atmosphere, of the way our eyes and brains process light. It's a reminder that we live at the bottom of an ocean of air, transparent yet substantial, protective yet invisible, revealing itself to us through the scattered light that colors each day. Rest in that knowledge now. The sky above you is blue for reasons you understand, following laws of physics that are simple and elegant and universal. The same scattering that creates beauty also creates information, connecting the local to the cosmic, the everyday to the profound. Let yourself drift now with the scattered blue light, those photons bouncing through the atmosphere, painting the world in peaceful color, a gift of wavelength and molecules in the particular miracle of Earth's atmosphere, gentle and eternal, the blue that has arched over every moment of human history, the blue that will continue long after we're gone. Sleep well, beneath the blue sky. Even in darkness, even with your eyes closed, the atmosphere continues its work, scattering moonlight and starlight, waiting for the sun to rise again and paint the world in blue. Rest now. The sky is blue, and you understand why. Good night.